Uh, Good afternoon, everyone. Today we're gonna present Keypoint community paper from ICCV 2021. Yeah. So this point, they present human and object pose estimation method that works on like a pose estimation that has both key points and fine-grained key points. And so what they do is they make the key points as a modeled graph, and then they use graph centrality to assign training weight to different part of the pose. And then with this trick, they kind of achieve the state of the art on human pose estimations with fine-grained annotations. I'll talk about all of them later. And then also another thing that they will do is that they generalize their pose estimator to other like object pose estimation, especially car pose estimation. And it's one of the few methods for car pose estimations. So here is like example of the human key point annotation with fine-grained annotations. Yeah. So recently there has been a new data sets on for human pose estimations, which they have like additional over 100 additional fine-grained annotation on the human face, hand, and feet. And using this data set, it's a little bit challenging for older methods because all of the older methods, they focus they kind of weight each key point equally, but in this kind of data set, like key points on the hands and fingers, they are not as important as key points in the shoulders and the waist. So this is one of the limitations for older methods. And also using this kind of data set, we can use human pose estimation for action recognition and intent prediction tasks as well, because like these annotations have a lot of key points on the face, hand, and feet of the person. And also another like older methods, one of them is ZoomNet, and this work. So the way that ZoomNet works is first it detects all of the key point, coarse key points, the key points that is not in the face or the hand of the person, and then it zoom in and then detects the additional fine-grained key points. But this method will take a lot of time. So the proposed method do all of this in parallel. And okay. Also, yeah, all of the previous methods, they suppose uniform importance of each key point, but if we follow that one, as you can see in this image, the face has a lot of key points, so the model will mainly focus on face and hands, and then it will maybe perform poorly for the rest of the body, which are also important. And so this method, the proposed, like this paper, they propose a key point weighting method that it will take into account the difference between coarse key points and the fine-grained key points. And yeah, so their contribution is a method that weighs the importance of key points and their connection in complex poses. And then also efficient implementation for fine-grained human pose, and they achieve real-time. Oh no, their method is much faster than the previous methods for human pose detection on proposed benchmark, and also they can generalize their methods to car pose estimations. Yeah, so recently in the human pose estimation, there will be proposed new data set, which consists of 133 key points with coarse key points and fine-grained key points. And also in human pose estimation, there are two types of the methods: top-down methods, which estimate person bounding box, then body joint location within that bounding box, and bottom-up, which is estimates the body joints first and then they group them. And the bottom-up method is more popular. and it has been introduced in CVPR 2016. But this method previously they had a problem with processing time. So the later bottom-up methods, they focus on the processing time and improve that. Yeah, here's an example of the Keypoint annotation from Cocoa whole body data set. Yeah, so they have like this coarse key points like shoulders, elbows, waist, and knees. And then they also have a lot of fine-grained key points in the hand, feet, and especially the face of the person. And for the car pose estimation, the newly released Apollo Car 3D dataset. This is also similar to Cocoa whole body dataset, which consists of 66 key points. Previously, car pose estimation dataset, they had around 9, 12 to 15 key points, but this one has more fine-grained key points. I think it's annotation. I think that they don't have. So sometimes, 2D. Yeah, it's 2D. Okay. Yeah, so they claim that this car pose estimation on this Apollo Car 3D dataset is better than simply like detecting 2D or 3D bounding box, because firstly you have more points to work on, and it may give finer details about the object in image than the bounding box. Also, yeah, there's one method for car pose estimation which named occlusion net, and this method works on like when in any image of the car, one part of the car is always occluded by other part, so you can just see some part of it, and they capitalized on that thing and then propose their method. And also another related work is key point weighting. So all of the previous works on the pose estimation, they work in the with less key point annotations. So they just assume uniform distributions. Or some of the methods that work with fine-grained regions, they just first detect the coarse key points and then zoom in and then detect the fine-grained region, which will take more time. Yeah. So here's the example of Apollo 3D car, and this dashed lines means it's occluded, it's not visible. Yeah. So this is the architecture of the proposed paper. Apparently, they don't do anything about base network or head networks. So their main idea is to add this training weight to the head networks, and then they will get better result. And their work is very heavily dependent of the CVPR 2019 paper, which do human pose estimation, but that paper they don't do pose estimation with fine-grained key points. So another difference is this fine-grained key points and these blue lines, which from the training data, they make training weights and then train their method with these weights.
So that training weight is UV edit?
Yeah. So that's like one of the biggest contribution of this paper, this training weight. Yeah.
But how do they calculate that weight?
Oh yeah, I'll talk about that. So because their method is mainly talk about that one. Yeah. So yeah, their base network is shuffle net, and then they have like head networks for which consist of the one convolutions followed by subpixel convolutions. And then their head networks train separately, and they use ShuffleNet pre-trained on COCO dataset for human pose estimation. And then the output of the first head network, composite intensity field, is like intensity component, and then key point location and uncertainty of the location, and the scale component SK. So this scale component estimate the size of the key point. So the size is so the size of the key point is very like directly proportional to, how can I say it? So here, as you can see, in the right side, the size of the key points in the waist and shoulder are much bigger than the face and the hand. So it means that the model will pay much more attention to these key points rather than these fine-grained key points, so that each key points will have like equally attention of the model. Because like if you use uniform distribution, then the model will mainly focus on the hands or face, and then it may do bad for the whole body. But when we like assign size to each key point, then the model.
So they are focusing on body structure rather than the detail.
Actually, they are trying to focus on everything equally. So that's why like they assign size of the key points, and then the training will focus equally and like predict everything equally. So that's like their main.
What's the difference between A and B?
Yeah. Okay, I'll talk about it after this. And then they have also composite association field, and this field this works on like it. This head of the network predicts the association between two vertices, so if they are connected or not. Yeah, and then this is a loss they will use for CIF head, and then they have like binary cross entropy loss for this forget it. For the intensity component, and they use Laplace loss for location, and then the size of the key point. So I think this paper is heavily dependent on the CVPR papers. They don't talk too much about these losses or their base network or head structure in deep.
Vision 1 through 3 are come from that.
Yeah. So that's why like I had so much difficulty understanding their methods before. And yeah, so here's the main part. So the graph centrality, usually the graph centrality is used to detect the important node of the graph. So people used it to like detect the important person among several people, especially in social media or that kind of stuff. But here, since we need to find the key point which is separate from other and should get higher value, that's why we inverse the graph centrality. Yeah, so yeah, they generally used to determine importance of the node in the graph. And also one of the way to measure the graph centrality is to calculate the shortest path from one vertex to all other vertex in the graph, and then normalize it all vertices. And also in this paper they used that method, and also they made ego graph of radius 3, and then they measure the centrality. So we go back to this. In the right side, it's like they use graph centrality for whole for this whole graph, if we count it as a graph for the whole graph, and then assigned weight to each key point. And in the right side, they used ego graph of radius 3. So for each vertex as a root, we calculate the shortest path to key points, which are like 3 vertex away from this key point, and then normalize over all that vertex in that 3 ego graph of radius 3, and then assign vertex. As you can see, the B is better because it assigned much more weight to important key points, especially like hips and shoulders rather than face and other stuff. Yeah, so here they use a harmonic average, and so they assign HV as a weight to each key point, and HV is calculated with 1/, Euclidean distance between that vertex and any other vertex in that ego graph. And also, yeah, as we said, that like key point weights obtained by normalizing the centrality measures. So summation of the centrality measure between any two vertex in that ego graph, and then they also assign weights to each key point for the training. Yeah, so as you can see here, there is like they have weight for each key points, and they have weight for each connection between two key points, and so that's how they get yeah, the weights for connection between two key points, and they normalize the sum of the edge to the total number of the edge, so that they they evaluate their methods on Coco whole body data set and Apollo Car 3D data set. So this Coco whole body data set, they use the previous key points of the Coco data set, and they add 160 fine-grained details. And yeah, and Apollo Car data is similar to that one. And yeah, so this is how they train their model. They use ShuffleNet pre-trained on MS Coco key point task without waiting, without their method. And then they trained their head networks on the this Coco whole body data set for 100 epochs, and then so here is a result of their detection on human body only.
So they don't explicitly have detection.
Yeah, they can use any bottom-up pose detection and then use their method to improve it.
Their input is input to the their anyway the input is all image.
Yeah.
And they can calculate this.
Yeah.
From the whole image.
So I think they get their the weights from training data set, and then maybe and then using this training, they use them for evaluation.
So can you present the CVPR 19 paper?
Yeah, actually.
Maybe next time.
Yeah, that would be better. So yeah, they like one of their contribution was state-of-the-art results, and as you can see here, they outperform all of these methods. But these methods are methods that they have been evaluated in Coco whole body data set, and that like CVPR paper they use Coco pose estimation data set, not whole body. So this is one of the difference. And then here is the result in Apollo Car. And also in this Apollo Car 3D data set, there are not much networks. And so there is only one, this CPM, which is very old method, and their method is, but they can compare it with human annotators, which is almost close. And then, so they use this detection rate, which calculates if predicted key point is within 10 pixel difference from ground truth. And also, yeah, they have so this ZoomNet is proposed by authors of the Coco whole dataset paper, they propose a paper and this network, and this proposed method, it's better than ZoomNet with AP and also time, and also they can change these thresholds to get better time, but with lower accuracy. So apparently that CVPR paper, they have new CVPR paper in 2021, and so the authors are the same. They made like, I think, first version and the second version, and then two of that author of the CVPR paper are author in this paper, and one new guy. Well, what's the name? Yeah.
Any other questions from the chat? No. Then let's finish here. It's over 1 hour. So how's your grading application?
I stopped recording, no?